Okay, so it's 11:20 on a Monday afternoon, a Monday morning. It's dull-ish outside. Half of you are jet lagged. Coffee was 50 minutes ago, so the caffeine is now out of your sympathetic nervous system. Lunch is a little way away. You're thinking I should have had that second Danish because it's So, perfect time for time series. So I'm going to talk. Really, Uma and Dima have both given very nice detailed overviews of machine learning and deep learning, particularly. I'm going to give a sort of somewhat broader, more general introduction to time series analysis with an astronomical bent to it. Machine learning and deep learning are really new. Time series analysis is really old. In fact, it's probably the oldest thing that we do in astronomy or have been done. This is a 1,000-year-old plot. Took slightly longer in those days to get them out. You also would do it on calf skin as opposed to paper. But what you're seeing here is a model of the solar system, or an idea of when you might be able to see the variations in planets against zodiacal division of the sky. So you've got the 12 houses of the sky divided up, and this is the moon, which obviously does a straight line. So there's no notion here of more sophisticated orbits. But it's quite sophisticated in that there's a realization here that you've got patterns, and some of them are regular and some of them are irregular, and there are sort of very common notions to a lot of the things we do with time series analysis today that are already inherent in this, even coloring bits of it. So we've been doing this for a long time. This is probably one of the earliest time series probably noted with measurements in the sort of sense that we would recognize today, certainly that we're getting from ZTF, because what we have here is we have dates and we have magnitudes and some observation about what the observation of those for were each one of those dates. And this is for the same source. This is Myra, discovered over about 40 years. They kept seeing it appearing, but they thought it was uninteresting because they said if the new star were outside the ordinary course of nature, it would tell us little about the constitution of the universe. So you're talking about a fixed model of the universe back then, and anything that appears, anything that's an outlier is completely uninteresting because it doesn't fit in with what our model of the universe is, that we believe in this static thing and this is just transitory and probably means a king's going to die or something like that, but nothing important. So we have a completely different view these days because we're now in this era where we have on-spinning disk available to you as members of the general astronomical public, probably at least about 1 billion time series for optical, radio, infrared, ultraviolet, X-ray, gravitational waves, neutrinos, anything you really want, just exploding and exploding. ZTF, the project I'm involved with, I'm the project scientist, and we did a data release. Our first data release about a month ago, 2 months ago, and that was 1.25 billion time series. I was at an LSST brokers meeting last week, and they're talking about 37 billion time series. So there's huge amounts of data we're going to have, and we really need to sort of try and understand how to analyze them. And with such large collections of data, what are we asking of them? Well, there are sort of three things, right? If we have just a few data sets, a few time series, we can't really do much with it. It's still, oh, look, this is an interesting single event. That's the sort of where LIGO is at the moment. Oh, look, it's another black hole merger. And we've only got 5 or 6 of those, so let's still understand what's going on, and everyone follows it and mines it to death. But if you've got, 100,000 RR Lyrae time series, you can start doing population behaviors. You can characterize these things in terms of some set of statistics or some sort of measures. You can categorize them, sort of say, well, those groups look together, look the same sort of thing. I wonder if the same thing physically is going on underneath with that, or if there's some reason for why those look the same through some sort of supervised learning. And then you can classify them. We start saying, well, we understand that that's a type 1 and that's a type 2, and maybe there's a type 1.5, and there's a type 1.7 or a type 1.8, depending, this sort of thing. We're also really interested in outliers because it's, well, maybe you'll get a Nobel Prize for that, but you'll get a Nobel Prize for that. So we want to find the things that look different from everything else, or look different from some definition of what normality is, in some statistical sense or some metric sense or whatever. So a lot of the things is we're doing outliers or anomaly detection, and there's a whole suite of machine learning dedicated to that. And then the other thing is we actually, we can come up with a nice statistical model for how something might be behaving, but what we really want to do is tie it back into a physical model. We want to have some idea of what it is fundamentally that's going on between these stars or between these neutron stars or black holes or whatever it is. And because we are physicists, essentially, we can make a prediction, and we're scientists, and we can see whether our model holds for that prediction or not. And if it doesn't, we throw it out, and we come up with a different model. So here's an example of some of the sort of phenomenology you see just in young stellar objects. We see periodic sources, we see sources which are multi-periodic, sort of quasi-periodic and symmetric, bursters, aperiodic dippers, quasi-periodic dippers, stochastic, and long timescale. So this is work that Anne-Marie Cody and Lynn Hellenbrand did with some Kepler data. That's why it's so nice. But it gives you some idea of the sorts of, that sort of first stage of categorization or what. We also sort of divide up our space, our knowledge space, with time series into a fairly sort of compartmentalized. This is Laurent Ayer's famous variability tree, and you can say, well, I'm up here, I see something varying. Do I think that it's coming from sort of something that's extrinsic to it, or is it an intrinsic process? Most of the things that we understand, or most of the things that we've classified in terms of variability in astronomy time series are stars, and you can go fairly far down this tree to some very detailed categorization of pulsating stars or things like that. And then at higher levels you have, eclipsing asteroids or eclipsing stars or something, where we've done less of that categorization, less of that classification to date. Most of this stuff is really easy because it's periodic, it's regular. Some of it is a lot harder because it's stochastic variability, and we have fewer tools for working with those at the moment. So with that sort of stuff in mind, there are some sort of basic concepts that we need to bear in mind when we do any analysis of astronomical time series or general in time series. So I'm going to go through some of these for a while. So first of all, let's agree what a definition of what we mean by a time series. So we're saying it's a set of time-tagged measurements, not necessarily one-dimensional. It could be a set of spectra that I've got, or it could actually be a set of data cubes that I've taken on successive nights, but they're time-tagged in some way, and there's some sort of observation error associated with them. Now, the first thing that makes this data set different from, say, a set of galaxy positions on the sky, or a catalog, is that this data is not necessarily IID, as Uma introduced, is independently and individually and independently distributed, because the data is sequential. So it's not as though each data point is independent of the other data points. What actually means is, because this is a time series, the value that I measure now is actually probably dependent on, in some way, or it's related in some way to the value I measured before. If I think of something sequential, that's, in more everyday life, speech, The words I'm saying now are somewhat dependent on the words I've just said to give you some idea. I'm not talking complete garbage, I hope. Or the probability that it's going to rain today is going to be dependent on the probability that it rained yesterday, which in Pasadena is 0, but if you're in Seattle or the UK or somewhere like that, it's going to be much higher. So we have this dependent. There is an arrow of time in our time series. There is a natural direction. So that's something we need to be aware of when we're doing our analysis. Another thing is that if I'm measuring heartbeat or if I'm measuring brain activity or whatever, and I end up with a medical time series, I'm probably fairly happy that the error model that I'm using for those observations, that sigma I, are all drawn from the same distribution, because it's not as though I'm going to have measured my heart, if I'm doing a ECG or an EEG, I'm going to do it within a single time frame. I'll get hooked up to the machine, and I'm sitting there for half an hour whilst the trace thing's going, and then they go, there's your time series. We don't really do that with astronomical time series. The bulk of the astronomical time series we look at, I'll get a data point tonight, I'll get a data point tomorrow night, I'll get a data point the next night. And tonight might be beautifully clear, and tomorrow night may be a little hazy, and Wednesday night might be completely cloudy, or the seeing may be really horrible because the Santa Ana winds are blowing up or something. So our conditions change from time to time to time when we make our measurements in astronomy. And what that means is that our data is not what's called homoscedastic, but it's heteroscedastic. So all the errors are not drawn from the same fundamental process or fundamental underlying distribution. They're drawn from different distributions. We believe it's a normal distribution, let us say, but the mean and variance of the distribution I use tonight may be very different from the mean and distribution that I might assume for tomorrow night. So that's something we need to factor into our analysis. Another thing is this term called ergodicity, which is not so important for regular time series, but the idea is that if I measure that the time series I have is representative of the overall process. So instead of getting a whole load together and taking an ensemble average, I can just look at the time average for one sequence. And so that means my sampling, what I can infer from a single time series for the process is as good as if I sample all over. A more fundamental one those are all fundamental, but a slightly more important one that comes more into the analysis, let's say, is this idea of stationarity. We assume for a lot of the time series we look at that the generating process is time independent. So the thing that is doing this, the joint probability distribution of all my variables, the unconditional probability distribution, is translationally invariant with time. So that means that the distribution I see now is the same as if I shifted it temporally by a day or a week or a year or whatever. And that's really what the definition of strong stationarity is. I can relax that a bit and say I'm only concerned, only want to assume that the mean, the variance, and the autocorrelation are constant. And that the second order moments are at least continuous, and that's weak stationarity. What that means is that the mean magnitude I measure for my star, I'm assuming, is not going to change with time. Or the variance is not going to be dependent on whether I observe it now or in 6 months' time or in a year's time. And a lot of what we do makes this assumption. White noise is a stationary process, an example. Now we have things like GSR 1915, which is a microquasar. So it's this sort of very highly active X-ray binary in the galaxy, which has 20 different variability states that you can identify in it. And these are coherent states. They are repeating, but this object seems to switch between them. There's a heartbeat state, and there's an outburst state, and whatever. But this is not random behavior. These are coherent for phases of time. So this is clearly an object where this notion of stationarity does not apply. Okay? There are these models as well more sophisticated time series models called Gaussian models. They're very popular for modeling stock markets or financial time series. And in those, variance is not a constant, it's a stochastic function of time. The variance is going to be a random variable depending on the time. And so these models are non-stationary. And there's a general thing about non-stationary time series that there's no fundamental reason why they have to be stationary in any limit. So there's no good statistical reason why a non-stationary time series may have to be stationary. So a lot of what we do with our time series, with those billion time series, is we assume that I can just measure the mean for each of those, and it's a meaningful quantity for each of those. And that may not be true with what we're doing. Now, there are ways to get around this. There are ways to at least enforce some sort of weak stationarity, not necessarily strong stationarity. And the easiest one is you just difference your data. So instead of looking at magnitudes, I'm looking at the difference between the magnitudes at a particular time. And if that doesn't work, I can go to a second order difference or a third order difference. I can detrend my data. If what's causing this, if I've got periodic modulation going through my data and that's the thing that's causing my mean to not be constant, obviously what I can do is I can fit some function through that and take that away, and then that leaves me with something which is, detrended and whatever. And we do that a lot. That's certainly a very popular thing in exoplanet searches. If I'm concerned that the variance is not so stable, maybe I can take the square root of my data plus some sort of term to make sure I'm not dealing with non-negative values, I'm only dealing with positive values, or I can take the logarithm or something, and maybe do some sort of linear transformation like that. I was reminded of this just with that last question to Dima about what happens if you have your data between some wild range and you normalize it. And that's what we're doing this. And I can always test the stationarity by looking at the autocorrelation function of the residuals and see if they look whatever believable. Sampling is another thing that we have a wide variety in. If I go over to, where are we? If I go over to the science library here, or look in the science library, the astronomy library here, and go to the section on time series analysis, I will find a vast array of books on time series analysis, from econometrics and all sorts of sciences. And most of those are for time series with even or regular sampling. If I then go to the shelf which deals with irregular time sampling literature, and it will be a shelf compared to the vast amounts of books that I'm looking at. But this is what we deal with far mainly in astronomy. We're dealing with uneven or irregular sampling. And this makes statistics nice, this makes statistics horrible, which is why people write textbooks on this and not on this. Though textbooks on this would be far more useful. So what do we do? Well, the first thing we do is maybe you look at your time series and go, well, it's not that irregular. I mean, we took the data roughly at the same time each night, plus or minus an hour. Maybe we can sort of just force it onto some sort of regular grid with a resampling. Maybe I can take a weighted average of the data and assume that I'm sort of putting it into some interval, and then I'm just going to use those data points. So the Catalina Real-Time Transient Survey, you take 4 observations within 40 minutes, but those change. But what you can do is what I could do is I can take the average of those and say, that's the observation for that night, and that's the observation for that night, and that's the observation for that night. Or maybe I can interpolate onto this regular grid again. Maybe I'll just put a linear interpolation or a spline, or a Gaussian process or something like that. And I'll talk more about those in a while. And so do that sort of thing. Well, yeah, you can. The problem with any of this regularization or resampling is that you're introducing, you're going to introduce new biases, and I may introduce a new source of error or a systematic error in what I'm doing. What I would really like is if there's a set of statistics or metrics or some way of dealing with what are called continuous time processes. So I have a model for what this thing is doing, because it's described by some differential equation. This is a first-order continuous autoregressive model, for example. And what I think of my observation is that they're just random samples or random pickings drawn from that continuous. And then there are ways I can do my process that way, and I can assume there are statistics that I can draw from this underlying process which are necessary for that. The ultimate goal, of course, is, wouldn't it be really nice if we can just take the Fourier transform of our time series, we can calculate the power spectral density, and that gives us all the information we need about our time series. It'll tell us at what scale the power is there, and then we can translate that and understand what that means in terms of physical processes or this sort of thing. Well, you know, I can maybe... Yes? Huh? Previous slide. Uh-oh, here's a problem question I knew. Yes? Yes. Yes, this is the Ornstein-Uhlenbeck equation. So this is it's a stochastic differential equation for a first-order continuous autoregressive process. Yes. It's because there's a thing called the E2 integral, which is, it's how, so this is the white noise term. And so there's it's a bit mean, yeah, something like that, yeah.
So actually, in the end, you can actually plug this equation inside a simple vector process for the behavior of the limit, right?
You can, and I'll show that in a minute, yeah, okay. Fourier transform, well, Fourier transform's horrible to calculate, maybe, especially if I've got discrete data and it's regular, I can just take the discrete Fourier transform of everything. If it's non-uniform, there is a thing called the non-uniform discrete Fourier transform, which I could use, and maybe I can use that to estimate, but it can be noisy. Maybe the autocorrelation function has the same information, it's just the Fourier transform. Maybe that's the thing I can work with. And if that's difficult to estimate as well, then there are things like structure functions which you can show are related in some non-trivial way, and there are nice estimators for the structure function. So I can actually maybe have some second or third generation estimator of this quantity fundamentally, which will tell me that sort of thing. Time series can be decomposed. We can actually, if I've got a stationary time series or process, I can think of it as a combination of a stochastic component and a deterministic component. And this is what Wold's theorem says from the late 30s. And so if I'm thinking about something like GSR 1915, I can identify those components which I believe are related to some sort of deterministic behavior, where even if it's chaotic, there may be some sort of regular or quasi-regular physical process which is comparing those, and that's states 1 through 8, and then states 9 through 15 or whatever. I can say, well, as far as I can tell, they're stochastic, they're completely random, and I can describe them statistically, but they're related to magnetohydrodynamics or some horrible turbulence process going on in the object and that sort of thing. So we can do these time series compositions, and there is, as I say, Wold's theorem means that we can actually do this in reality. Right, that's enough theory. Let's get on to some practicals. So what do? Well, we sort of say, those two things look different. I want to find more of these, and I don't care about these. How can I do that? And so we do these features. We extract data features. The other problem, of course, as I've been saying, is that, well, this is noisy, gappy, heteroscedastic. horrible. And it may be that I've got 30 data points here, and maybe I've got 150 data points here, and I want to compare the two together in some machine learning algorithm, and so I need to come up with a homogeneous representation. And so this is why we do it in terms of statistical features or measures. So I can take the slope, I can take the amplitude, I can decompose this into a set of Fourier series, or I can do a Fourier series decomposition of this and look at the relative amplitudes of terms and whatever. And so there's quite a bit of literature on this. The people in the room who've worked on this sort of stuff. You know, we can look for time scales, we can take a periodogram of the thing, we can look at variability, we can look at morphology, take the statistical moments. We can fit trends and see if we can understand it. As I say, we can do these sort of model fits as well, and trying to understand what's going on. And then we take our time series, we do the representation, and then we do plots of one against the other, and sort of say, oh, well, we can sort of see some groups here. Again, this is the work from Cody and Hillenbrand. So the sort of quasi-periodicity versus flux asymmetry, and they're sort of identifying some of those things in those, and then they sort of relate and say, well, how does that tie into the physical time scale of the behavior or the amplitude of the behavior, and sort of do that sort of thing. Yeah, we can do that. And then you can break it up into classes and say, well, if we can do... we can define classes in terms of models that we actually understand, or we can do the sort of unsupervised classification and sort of say, well, this looks like a high amplitude thing versus a low amplitude thing, and you know, then we sort of tie it into more physical things. Not all features are equal, however, and there's been a number of work or a number of papers. So in time series analysis, particularly stellar time series analysis in astronomy, there's a sort of general set of features that are used, which is Joey Richards from 2011, Josh Bloom's group, and there are libraries out there which will happily calculate these for you, like FATS and other things. But these are highly correlated because, you know, there's only, what are you measuring? When you're measuring variance or scatter, or if I'm measuring location or median or you know, mean amplitude, that sort of thing, I'm measuring the same sorts of things. I'm just measuring them in a number of different ways. And so maybe I don't need 60 or 70 parameters to do this, I only need some. So you can do these feature relevance arguments and figure out which the best features are. And unsurprisingly, for periodic variables, it turns out that the period is the best variable. And there's a lot of effort, again, you know, most of our time series analysis in astronomy are looking at periodic variables, because aperiodicity is much trickier. So there's a lot of effort, there's been a lot of effort into figuring out how to find periods. You can maybe do something like Lomscombe-Gill, where you do you try and fit your time series in terms of some sort of, well, they use trigonometric basis function, but it could be some sort of orthogonal basis function. Get your best fit and find what the periodogram looks like. You try your trial period. Or maybe you take a phase folding method, and then you look at some statistic in the phase folded space that minimizes dispersion, and plot a variogram where it's your statistic against your test frequencies that you're looking at, and either it's a maximum or minimum, and that gives you the thing nicely phased up. So there's a whole literature on those. Part of the problem is there's no single algorithm. So, I mean, which is the best algorithm to use? There are neural networks which will do this now. There are Bayesian methods. There are methods which are computationally very expensive, methods which are computationally very cheap. Does it matter on the class of object I'm looking at? Does it matter on my sampling? Does it matter on how accurate I want to be? it's been shown that in a lot of the machine learning algorithms, particularly those ones where people are doing classification of time series, 75% of the computation goes on to working with periodic features, and half of that is getting the right period. If you get the wrong period, you're going to misclassify. And there's a 22% misclassification rate for periodic variables if you get the period wrong. So this could be very important to the science you're trying to do, particularly if you're after one of those outlier objects. If I misclassify it and it goes into an intermediate of space because I got one of these features wrong, because the period is wrong, that's going to be problematic. Yeah, talked about that. And also, we quote these periods. How trustworthy are them? People very rarely or tend to not put error bars on the period that they've calculated. They just sort of, well, we got a period of, whatever. And we know there are objects where it doesn't have a single period, or the period changes. Blaschko effect in RI Lyary. Happily going along, suddenly it's got a slightly different period, and that changes the amplitude. Or close binaries, or things where the period changes. All sorts of problems that makes period not a single easy number, and yet we use it as though it is. So what we found was that there's no general algorithm, there's no silver bullet algorithm. If you use Lom-Scargill, or actually if you use AOV or conditional entropy or something like that, maybe across the suite of stellar variables you're going to be about 60% accurate. You're never going to get greater than that. What you need to do is you need to actually put some domain knowledge in. You say, I am looking for RR Lyary, which have a sawtooth waveform, and so therefore the best algorithm to use is this. Or I'm looking for something that's very sinusoidal, and so therefore using Lom-Scargill makes sense. Or I'm looking for something that's an eclipsing binary. There is specific algorithms which work in specific cases, whether you're looking at regular sampling or signal-to-noise ratio, performance constraints, and all this sort of thing. So something to be aware of with these time series analysis. A new way, or relatively new way, of actually working with time series is people are moving away from these single feature representations and starting to play with, featureless representations, things like Gaussian processes. And this is particularly favored within the exoplanet community because of the interpolation and because you can do some very sophisticated modeling. So the basic idea behind a Gaussian process is that my data is drawn from some overarching normal distribution which has a mean function and a covariance function, and the covariance function contains all the information that's required. But it actually describes a family of curves that will be constrained by the form of this covariance function. And so I can, I have a set of data points, and there's any number of families of curves which could potentially go through it, and I can constrain the values down of what those are when I've done my learning. The covariance function will have a functional form. I can put my error estimates into this, and there are a set of hyperparameters that I can learn by maximizing the log marginal likelihood. And the other nice thing about this is that I can make prediction to fill in the data points or the places where I don't have data points, or maybe I can even do forecasting for outside of the range I'm looking at. And again, it's well constrained. It follows Gaussian statistics. Again, I just need to know the functional form of this covariance function, and then I can work very nicely with it. So again, boils down to what choice of covariance function you want. If I just really want to do equivalent to least squares, I can use a squared exponential. If I want to do something more sophisticated that I believe is autoregressive, I can use this Ornstein-Uhlenbeck thing. I can put a periodic function in there, periodic kernel, if I got periodicity in. There are some libraries which work very fast. There's this Celerite library in Python. If I can express my kernel function in this sort of exponential sum of exponential forms, this is a very, very fast library for working with this. There's a lot of good stuff with these. A type of model that I might also want to think about is an autoregressive model, particularly if I believe I have dependencies in my data. Simplest one is random walk. This is just a random draw from something. If I constrain it in some way, I end up with so I can have a purely random one, or I can have it dependent on the previous value. Yep. And so this is Brownian motion of some fashion. So this is what's called a first order model because I'm only dependent on my previous value. If I leave this unconstrained, it could go off. I can put I can constrain the value of that, and that gives me a drunkard's walk or something like that. I can have it as a first order term or higher order terms. I can maybe modulate where the noise is coming in as well to give me a moving average. These are becoming, again, increasingly popular, particularly for aperiodic variability. And I'll mention AG in a minute. They're also coming from the world of finance, where people believe that they can use ARIMA or these RFEMA models for modeling stock market again. There's a nice paper by Eric Feigl from earlier this year where he's showing how these can be applied to astronomy. It's a super family of models where you have this autoregressive as the first one, and then you go up to these ARMA models, which are a subset of these ARIMA models, which are a subset of RFEMA models. These are all discrete time models. There are continuous time equivalents, which have a C put in front of them. So instead of you have ARMA, you have KARMA, you have CARFEMA, this sort of thing. But you can fold these into Gaussian processes. So there's a bit of math which says that a process can be said to be autoregressive if the power spectrum of the kernel can be written in this form. There's a type of kernel in Gaussian process called a Matern kernel, which has this form, and you can calculate it, and it has that form. And so you can put one of these autoregressive models quite easily into your Gaussian processes. And it turns out that there's I don't have it there. This thing here, which is this first-order autoregressive model, is also what's called a Matern half-kernel, so I can write a Gaussian process which fits this very nicely. Quasi-variability is modeled as one of these autoregressive models, damped random walk. There are problems with it, but it's the basis for a lot of stochastic models of variability in astronomy. Those problems mean people look for higher order. Maybe I can go to one of these KARMA models, these 2-1 models, higher order. What this gives me is quasi-periodicity. Sort of think of this model as a damped harmonic oscillator. So maybe what I'm seeing in the time series when I'm looking at quasi-variability is some combination between a damped random walk and a damped harmonic oscillator, and maybe I've got some combination of those behaviors going on together, which means maybe this is why I sometimes see this sort of very quasi-periodic behavior in something that shouldn't show it. So if you're interested in binary objects which are showing stochastic variability, that's sort of really where the sort of cutting edge of a lot of this sort of analysis is. A lot of this stuff is, a lot of these models of time series where I'm trying to look for features for the sake of classification is discriminative. What I would rather have something is where I can learn the shape, learn the conditional distributions, and then these are generative and they support these sort of predictions and they tell me more about the underlying behavior. And Gaussian sort of processes fall into that camp, because what I really maybe I'm interested in is forecasting. So predicting periodic behavior is trivial. I mean, you know what a periodic source is going to do going forward. Predicting aperiodic is much more interesting, particularly if it's chaotic or stochastic. Stock market, climate change, epileptic seizures, earthquakes, that sort of thing. I'll talk more about that on Wednesday, and the various techniques that are used to do this. But we're now at the stage, I think, where we have the data and the models and know how to go forward to this, particularly for now using deep learning models for time series. This is a nice paper from Brett Knoll from, again, Josh Bloom's group last year, where, as Demas says, the advantages of deep time series, I don't need to worry about the features at all. I can just learn them straight from the data. It's all data-driven, and there are networks out there ready for sequential data. This is how Google Translate works, or how some of those, let's reproduce the music of Chopin or Bach. They're all based on this idea. It's a deep model that's learnt the sequence, that's learnt the behavior, learnt the features, puts it together. And so then you can reproduce what a time series maybe looks like realistically. I'll talk again more about that on Wednesday. So traditional time series analysis in astronomy involve this idea of describing it through features, which you then put into the machine learning. Didn't talk much about this, but we assume Gaussian tails on those features, and we say, well, if it's a 5 sigma thing, it's an interesting one to do, but little predictive power, no real idea maybe for interpolation. Data volumes, billions of time series, mean we can now model individual sources as well as the populations. I can capture full time series behavior as a result. I can do these very sophisticated interpolations, which probably means I'm going to be better identifying extrema. And the sort of next generation surveys, things like ZTF and LSST and SKA and whatever, are going to give us an even better handle on all that. So I think I'll leave it there for the moment. Okay?